तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we were considering what is a reflexive closure of a binary relation, symmetric closure and transitive closure. Let us recall the definition. Let R be a binary relation on a set A. The reflexive closure of R is the relation R dash such that R dash is reflexive, R dash contains R for any reflexive relation R2 dash. If R2 dash contains R, then R2 dash contains R dash. That is, the reflexive closure of a relation R is the smallest reflexive relation containing R. Similarly, we can define symmetric closure and transitive closure. As a graph, we have seen that if you have a binary relation represented by a graph, to get a reflexive closure, we have to add the self loops at every node. And to get the symmetric closure, if there is an arc in one direction, we must add the arc in the other direction. To get the transitive closure, if there is a path between some nodes, then you have to add the arc corresponding to that path. This is what we have seen in a rough manner. And we considered the reflexive closure. Let R be a binary relation on a set A, then reflexive closure of R is denoted by R union E. Then we have also seen what is meant by the converse of a relation. If R is a binary relation, whenever you have a pair xy in R, you have the pair yx in RC. Then we also consider some properties of the converse relations. This also we have already seen. If R is a binary relation on a set A, then R is symmetric if and only if R is equal to RC. Now, let us consider this portion. How do you define the symmetric closure? What is the symmetric closure of a binary relation R? Let R be a binary relation on the set A, then the symmetric closure of R is R union RC. R is a binary relation on a set A, then the symmetric on A, the symmetric closure of R is given by R union RC. How do you prove? What is the symmetric closure? The symmetric closure should contain R, it should be symmetric, and any other symmetric relation should contain the symmetric closure of R. So, suppose R dash is equal to R union RC, then we have to show that the symmetric closure is R dash, symmetric closure of R is R dash. Now, what are the properties of R dash? R dash contains R, this is the first property, that is true, and R dash is symmetric, R dash is symmetric. Why? Because look at this result, R is symmetric if and only if R is equal to RC. Now, what can you say about R union RCC, the converse of this, by the results which you have seen earlier? If, let us see, R1 union R2C is R1C union R2C, okay. B, making use of this property, R union RCC is RC union RCC C, and that is nothing but RC union R. So, the converse of this is equal to this. So, R dash is symmetric. Now, the third part is, let R2 dash be a symmetric relation containing R. Then we have to prove R2 dash contains R dash. Now, let AB belong to R dash. What is R dash? R dash is R union RC. So, if AB belongs to R dash, there are two possibilities. AB belongs to R, or AB belongs to RC. Now, R2 dash contains R. So, AB belongs to R means AB will belong to R2 dash, because R2 dash is a symmetric relation containing R. So, if AB belongs to R, R2 dash will contain that pair. So, AB belongs to R2 dash. Now, if AB belongs to RC, what does that mean? BA belongs to R, and because R2 dash contains R, from this you will conclude BA belongs to R2 dash, but R2 dash is a symmetric relation. So, from this you conclude AB belongs to R2 dash. So, whenever you take a pair AB belonging to R2 dash, it also belongs to R2 dash. So, R2 dash contains R dash. Okay. So, the third property is also satisfied. So, the symmetric closure of a relation is given by SR is equal to R union RC. Now, let us consider the transitive closure. What is a transitive closure? When you have a path, as when you represent the relation as a graph, when you have a path between some nodes, the transitive closure will contain the arc between the two nodes. This is the idea of a transitive closure, and we have already seen that in a communication network, if direct connection is denoted by an arc, then the transitive closure represents all the pairs of nodes from which from the first node you can send a communication to the second node. This transitive closure has lot of practical applications. Now, the transitive closure is given by this. Let R be a binary relation on the set A, then the transitive closure of R is union I is equal to 1 to infinity Ri, that is equal to R union R squared union R cubed union etc. Now, we have to prove this equality, that is TR is equal to R union R squared union R cubed etc. And this you represent I is equal to 1 to infinity R power I. Now, we prove it in two parts. First, this is contained in this, and then this is contained in this. So, first part is we prove that union I is equal to 1 to infinity R power I is contained in TR. This is what we have to prove. Now, to prove this part, use induction. Use induction. R is contained in TR by definition, isn't it? R contained in TR by definition, because the definition of R is it contains R, it is transitive, and it is the smallest such relation. This is the basis class. Now, the induction class, induction portion of it, suppose R power n belongs to TR. To show r power n plus 1 belongs to Tr. This is the induction portion of it. Now, let AB belong to r power n plus 1, that is r power n into r. When can you say that AB belongs to r power n plus 1? When there exists a C such that AC belongs to r power n and CB belongs to r. When you say AB belongs to r power n plus 1, that means there should be a C in A, this is all defined on a set A. So, AC belongs to r power n and CB belongs to r. Now, by induction hypothesis, this belongs to Tr and this also belongs to Tr, because anyway r is contained in Tr. So, AC belongs to Tr, CB also belongs to Tr, but Tr is a transitive relation, Tr is transitive, therefore, AB belongs to Tr. So, we have seen that if you assume r power n belongs to Tr, r power n plus 1 also belongs to Tr. So, union of I is equal to 1 to infinity r power I is contained in Tr. So, this portion we have proved. The other way around, we have to show that Tr is contained in union of I is equal to 1 to infinity r power I. This is the second portion. How do you prove that? First we prove that, prove union of I is equal to 1 to infinity r power I is transitive. How do you prove this? Suppose you have AB belonging to some r power s and then BC belongs to some r power t. AB belongs to r power s means AB belongs to this union. BC belongs to r power t, it also belongs to this. Now, what can you say about AC? In that case, AC will belong to r power s into r power t, that is equal to r power s plus t. AC will belong to r power s plus t, that is AC also will belong to union of I is equal to 1 to infinity r power I. So, when you have two pairs AB and BC belonging to this, you also have AC belonging to this, and when this condition is satisfied, you say that the transitive property is satisfied. So, we have proved that I is equal to 1 to infinity r power I is transitive, and I is equal to 1 to infinity r power I, obviously it contains r power 1. So, the right hand side, this is a transitive relation containing r, and by definition of Tr is contained in any transitive relation containing r. It is the smallest transitive relation. So, this is a transitive relation containing r, and by definition of Tr, any transitive relation containing r should contain Tr. So, we get this result, Tr is contained in union of I is equal to 1 to infinity r power I. So, these A and B together give us this result, that is Tr is equal to union of I is equal to 1 to infinity r power I, r union r squared, r cubed, etc. Let us consider some example. Consider a set of non-negative integers and a relation R such that x is related to y if y is equal to x plus 1. That is, any number I will be related to I plus 1. Define R like that on natural numbers. What is the transitive closure of this? What is the transitive closure of R? Now, we have seen that R squared means x will be related to x plus 2 for any x. R power s is x is related to x plus s and so on, and TR is union of I is equal to 1 to infinity R power I. So, what is that relation? It is less than relation. So, TR is the less than relation. Now, if you have this relation, set of human beings, then R denotes the relationship x related to y. X is the child of y. Then what is the transitive closure? R. What is the TR? This is the relation x is related to, or this represents a relation x is the descendant of z, x TR z, means x is the descendant of z. Now, let us see. Now, what about this n we have considered is an infinite set? What about the finite set? Let R be a binary relation on a set A, where A has n elements. Then you can show that TR is equal to union of I is equal to 1 to 2 power n squared Ri, where R is a binary relation, on A, on a set A, and A has n elements, where n is a finite number. Earlier we have seen that with n elements, if you look at it as a graph, you can see that with n elements you have a graph. If it is a relation, you will, the ordered pairs will be represented by arcs. So, you can have maximum n squared arcs in such a graph, that the maximum number of ordered pairs in a relation is n squared, and any relation you can have each one of the pair present or not present. There are two possibilities. There can be maximum n squared pairs, and each one of them may be present or may not be present in a relation. So, that gives you 2 power n squared possibilities. So, maximum you can have 2 power n squared distinct relation on A. So, this R power 0 is the equality relation, that we are not bothered now. We are start from transitive closure, we start from 1 to. So, if you consider R squared, R cubed, etc., up to R power 2 power n squared, R power 2 power n squared plus 1, among this set this will get repeated. Okay. So, you can have at the most R power, you can have at the most 2 power n squared distinct relation. If you consider R power 2 power n squared plus 1, this will be one of these relations only. So, it is not necessary to consider more than this. So, TR is given by this. TR is union of I is equal to 1 to 2 power n squared Ri. Not only that, you can see that in this case TR is union I is equal to 1 to n R. We need not even consider up to, when n is finite, then the underlying set is a finite set. TR, you have to consider only I is equal to 1 to n R power I. Why? You can see that TR is nothing but I is equal to 1 to, you need not even consider up to 2 power n squared. It is enough if you consider up to n. Why? Because what is really TR? It is a transitive closure. That means if R is represented, by a directed graph like this, say some graph, whatever it is, any path in TR, any path you also have an arc, that is TR, isn't it? Now, any path in R power 2 power n squared, if an element is R power I, if an ordered pair x comma y is in R power I, that means between x and y there is a path of length I, that is what it means. Now, this is R, in the we will consider the transitive closure, but before that, if this represents R, xy is an ordered pair in R power I, means there is in R there will be a path between x and y of length I. Now, if you have a path between two nodes, if you have a path between two nodes, something like this, from x to y, directed path, remove all the cycles from that, still there is a directed path from x to y. Earlier we had a path like this, a directed path which was not simple like this. Now, remove the cycles from this, then you get a directed simple path from x to y. What can be, so whenever there is a path between x and y, directed path between x and y, you can get a simple path between x and y by removing the cycles. And what can you say about the length of this simple path? Even if it visits all the nodes and comes back to x, it will be of length n only. So, the length of such a simple path will be at the most n when you have n elements in A. So, we need not even consider up to 2 power n squared, it is enough if we consider I is equal to 1 to n. So, in the definition of TR, whenever there is a directed path, it should be replaced by an arc. But we know that if you have a directed path, by removing the cycles, you can get a simple path between x and y of length less than or equal to n. So, you can add the arc in the transitive closure. So, TR is nothing but I is equal to 1 to n R power I. This gives us a very simple procedure to find the TR. Now, we have already seen that. Take this simple one, simple binary relation having just two arcs. So, what is the transitive closure of R? This is R, and what will be the transitive closure of R? It will be whenever there is a directed path, you have to add the arc. So, the transitive closure will be this. Now, if you represent the adjacency matrix of R like this, what will be the ABC? What will be the adjacency matrix? A to B there is an arc, B to C there is an arc. So, this is the adjacency matrix of R. this suppose I denote it by A, then what can I say about A square? What can I say about A squared? 0 1 0 0 0 1 0 0 0 multiplied by 0 1 0 0 0 1 0 0 0. If you multiply, what do you get? 0 1 0 multiplied by this is 0, this multiplied by this is again 0, this multiplied by this will give you 1, and the rest of the element, this multiplied by this is 0, this multiplied by that is also 0, and so on. So, R squared represents A square. Now, if you consider the graph or the binary relation A, B, C, this is R. R squared consists of only one arc between A and C. Any path of length 2 is replaced by an arc. So, R squared has this, which is represented by this matrix. Now, what about R cubed? R cubed, there is no path of length 3, so R cubed is the empty relation, that is obtained by multiplying R cubed is R squared into R. So, that is obtained by multiplying this, the matrix representing A squared and A, that is 0 1 0 0 0 1 0 0 0. So, if you multiply, you will see that that is the 0 matrix. Okay. So, we see that R, which is this, is represented by 0 1 0 0 0 1 0 0 0, and R squared is A, B, C, and this is represented by 0 0 1 0 0 0 0 0 0. R cubed is just empty relation and represented by the 0 matrix. So, the transitive closure of R is R union R squared union R cubed, union of I is equal to 1 to n R cubed, that is the you find the union of these three matrices, union of these three matrices, you will get 0 1 0 0 1 0 1 1 1 0 0 1, here you have 1, here you have 1 0 0, and that is nothing but this A, B, C. If you represent, there is an arc from A to B, there is an arc from A to C, there is an arc from B to C. This is the transitive closure. So, you can get the transitive closure by matrix multiplication like that. How much time it will take to calculate the transitive closure? So, R is a binary relation represented by the adjacency matrix, and this is of size n by n. Okay. Then, to calculate the transitive closure of R, you have to find A squared, A cubed up to A power n. How much time it will take? To multiply two matrices of size n by n, you require order n cubed operations. To multiply two matrices of size n by n. Like that you are multiplying once, twice, thrice like that, n minus 1 times actually. So, you are performing this matrix multiplication order n times. Order n times this matrix multiplication is performed. So, totally it will take order n power 4, because addition will take some time, but the total time is, this is the predominating factor. So, order n power 4 time it will take to find the transitive closure of a relation. There are very good algorithms to find the transitive closure, like the Warshall's algorithm, and Warren's algorithm. Maybe we will consider them later. They are very good algorithms, very efficient algorithm for calculating the transitive closure. They are very simple also. They take only order n cube time to find the transitive closure. Okay. Now, let us consider some properties connecting the relations, that is what is the symmetric closure, what is the transitive closure, and how they are related and so on. If R is reflexive, then SR and TR are reflexive. If R is symmetric, then RR and TR are symmetric. If R is transitive, then RR is transitive. Now, let us just, these are very simple and straightforward. Let us consider the first statement alone. R is reflexive, then SR and TR are reflexive. R is reflexive would mean R is represented by a graph, say like this, some directed arcs. If it is reflexive, you will have self loops at every node. Now, to get the symmetric closure, whenever there is an arc in one direction, you will add the arc in other direction. This is not going to affect the self loops in any way. Those self loops which are originally there are going to be there still. So, if you consider the symmetric closures, that will still be reflexive. And similarly, consider the transitive closure of R. The transitive closure of R, when you have a path between two nodes, you will be adding a edge between the two nodes. And these self loops which are originally present, they are going to be still there, they are not going to be affected, and so the transitive closure also will be reflexive. So, similarly, we can prove the other two parts, B and C. R is transitive, then RR is transitive. Now, let us consider this, these relationships. Let R be a binary relation on a set A, then RSR is equal to SRR, RTR is equal to TRR, TSR contains STR. How do you prove that? Let us take one by one. RSR is equal to SRR. RSR is equal to SRR. What is this? What is this? Take R, first find the symmetric closure, then find the reflexive. I will write like this so that it is clear. First find the symmetric closure and then find the reflexive closure. Here first find the reflexive closure, then find the symmetric closure. They are all equal. Either way you can do. First find the reflexive closure, then find the symmetric, or find the reflexive, find the symmetric and the reflexive. Either way you can do it. So, what is R? Okay, I will write R like this. RS R is equal to reflexive closure of what is SR? SR is R union RC, and that is equal to reflexive closure of a relation is R union RC union E. You are adding the equality relation. Now, what can you say about the symmetric reflexive closure of R? SRR is equal to, it is a symmetric closure of, what is RR? That is R union E. And what is this? This is equal to R union E union R union E C, that is equal to R union E union R C union E C. Equality relation is just the set of pairs of the form XX. As a graph, if you look at it, it is just consisting of self loops at every node. So, EC is the same as E, EC is the same as E. So, you need not have to write it twice. So, this becomes equal to R union E equal to RC, R union E union RC, and of course, because of commutativity you can write it as RC union E. So, you find that this and this are equal. So, you get reflexive closure of the symmetric closure of a relation is the same as the symmetric closure of the reflexive closure of that relation. That is the first part. Look at the second part. We want to show that the reflexive transitive closure of a relation R is the same as the transitive reflexive closure of R. That is, what we want to prove is this: RTR is equal to TR R. Now, what is RTR? RTR is R of TR, and we know that TR of R, that is the transitive closure, is R union R squared union R cubed union etc. And the reflexive closure of that is E union R squared union R cubed etc., where E is the equality relation. Now, we want to show that this is the same as this, that is the transitive reflexive closure of R is the same as this. But before going into that, let us make some observations. E power I is the same as E for any I, where I is an integer. What does that mean? If you take the equality relation that consists of just self loops, right, and if you take any power of that, that will be the same as the original equality relation. So, E power I is the same as E for all I. For all I, and RE is the same as ER is the same as R. What does that mean? Suppose E is the cell relation consisting of self loops, equality relation. Suppose it is on some set ABCD, and another relation is there on ABCD represented by R. So, this will have some marks. Now, what is the concatenation of this and this? What is the composition of this and this? ER. First this and then this. That will mean C to C. If you have C to C you will have. Of course, this, let me say it is like this: C to C, then here you have C to D. So, in the composition relation you will have an arc from C to D. Similarly, B to B you have, and then here you have B to C, and when you combine the relation, the concatenation of the relation will have B to C. So, E into R will be the same as R. Similarly, if you look at RE, an arc in RE will consist of a pair BC and then CC here. That will essentially compose of only BC. So, an arc from here to here, then a self loop followed by a self loop. Combine them together, that will be just an arc from B to C. Similarly, an arc from C to D combining with the self loop here will give you only the arc from C to D. So, R into E also will give you only R, E into R also will give you only R, and we also know that e power I is equal to E for all I. Making use of this, you will realize that T of R will be T of, what is the reflexive closure? This is R union E. So, T R of that will be R union E union R union E squared union R union E cubed and so on. And we know that e power I is E for all E, and then R E is equal to E R and so on, and e power I is the same as E, R E is the same as E R. So, making use of these results, this will essentially reduce to E union R squared union S. And this we have earlier seen that is nothing but R T R. So, we see that T R R is the same as R T R. Now, let us come to the third portion. The third portion is not equal portion, it is contained. T S R contains S T R. How do you prove that? We want to show that T S R contains S T. Now, this can be proved in this manner. Take the symmetric closure of a relation R. S R will always contain R. By definition, S R contains R. Now, take the transitive closure on both sides. So, T S R will contain T of R. Now, on both sides take the symmetric closure. So, S T S R contains S T R. But T S R is already symmetric. It is a symmetric relation, because first of all you are taking the symmetric relation and then taking the transitive closure. That symmetric property will not be affected by that. That we have seen earlier. So, this is a symmetric relation, and taking the symmetric closure of that does not make any difference, you get the original relation itself. So, because this is symmetric, these two are the same, and because these two are the same, you can write it as like this: T S R contains S T R. So, we prove the third part, and the first two part it was equality, the third part it is contained in. Let us show why it is contained in. Take the less than relation. What is T S of less than relation and what is S T of less than relation? Look at this first. Less than is a transitive relation. So, T of less than is the less than relation only, and the symmetric transitive closure of that is the symmetric closure of the less than relation, which is the not equal to relation. This is the less than relation on the set of non-negative integers, say. So, ST of less than is not equal to relation, whereas if you say TS less than, what is the symmetric closure of less than relation? That is the not equal to relation. And what is the transitive closure of this? That is the transitive closure of the not equal to relation, which is the universal relation. Universal relation on the set of non-negative integers. They are not the same. Self loops are absent here, self loops are present here. Okay. So, that shows that they are not equal, but Ts less than this will contain this. So, Ts less than contains St less than. So, it is the containment in this case and not the equality. There are examples to show that they cannot be equal. Now, generally you say that if R is a binary relation on a set A, then R plus, which denotes the transitive closure. Transitive closure is usually denoted by R plus. Instead of TR, many times you will use the notation R plus, that is the transitive closure. And R star is read as R star, that denotes the reflexive transitive closure of the relation R. So, instead of RTR, you will say that RTR is TRR, that we have seen. So, instead of saying that, you use R star. These transitive closure relations are really very useful in many cases. We will consider one or two applications. One is, consider a set of procedures. You have a set of procedures P1, P2, P3, etc. P and say. Then you represent like this: Pi R Pj if Pi calls Pj. If Pi calls Pj as a subroutine, say, then you say Pi R Pj. Then what does Pi R plus, say, Pk represent? What does this represent? See, Pi may call Pj, Pj may call Pr, Pr may call Pk, and if you say Pi R plus Pk, the set of such Pk's are the set of procedures which will be called when Pi is executed. When the procedure Pi executed, if you get Pi R plus Pk, that means Pk will be invoked during the execution of Pi. And what does Pi R star Pk represent? Of course, because this will represent the reflexive transitive closure. So, it will also include Pi. Here this may not include Pi. This is the set of procedures which will be active at some point when Pi is invoked. When Pi is called, the set of procedures will be active at some point of time is denoted like this. Now, when do you say that Pi R star Pi? Of course, reflexive closure will always contain Pi, so this will always hold. But if you say Pi R plus Pi, what does that mean? It means that during the execution of Pi, it invokes itself either directly or indirectly. Pi may call itself, or Pi may call Pj, and Pj may call Pi. Whatever it is, in that case Pi is recursive. Pi is recursive. It is a recursive program, directly or indirectly. So, this is one application. Usually this sort of a notation is also used in grammars. This star and plus we have already seen when we defined sigma plus and sigma star. Okay. So, in grammars this again, this notation is used. Suppose you have a string, say some A1 n, and some portion of it is, say I will denote it by u, is replaced by a rule u goes to v, say. So, from this string you get this, if I write as W1, it is a string over some alphabet, and if u, a portion of it is replaced by v, this u is replaced by v, but the rest of the string will be there, then you get W2. This is usually denoted by W1 derives W2. This represents a relation between strings, and this is called directly derives. This is if W1 derives Wn by this step, that is represented by this notation, which is known as the reflexive transitive closure. So, if it is W1 is derived in one step, you call it as directly derives. But if you have, say, W1 deriving W2, then W2 deriving W3 in one step, and so on, until you get, say, some Wn. Each is obtained from the previous one by the application of a single rule, and this you write as W1 star Wn. That is, this star you call this as derives, or in other words, if you get W2 from W1 in one step, you write W1 derives W2. If you get W2 W1 in several steps, Wn from W1 in several steps, you write it as W1 double arrow star Wn. This denotes derives. Okay. This denotes directly derives. This also represents a relationship between the strings. This also represents a relationship between the strings, and generally we have Wi star Wi, because each string is derived from itself, that is what we have. So, generally we say that, you can easily see that this is the reflexive transitive closure of So, to find out the communication paths in a communication network, all the pair of nodes which can be connected, or from all the pair of nodes from where from one node you can send a message to any other node, you have to calculate the transitive closure. And here again, like in grammar, you have this derivation. Even in automaton, which is a corresponding acceptance device for a grammar, you have these relationships, and you may be making use of this in several parts of computer, several subjects in computer science, and transitive closure is a very important concept. That is why people have spent time in finding efficient ways of finding the transitive closure. As we have already seen, if you represent the relation by the adjacency matrix, then if you calculate the transitive closure in a naive manner, then you may require order n power 4 times, because The adjacency matrix will be represented as a n by n Boolean matrix, and you may have to calculate a squared, a cubed up to a power n, find the sum. But there are other efficient methods like Warshall's algorithm and Warren's algorithm, where you need not go through all those steps. It takes only order n cube time. So, we have considered some closure properties of relations like reflexive, transitive and symmetric closure. There are other aspects of relations like partial order, linear order, well order, lexicographic order on strings and so on. They are also very useful in certain things. Then there is an equivalence relation, which is also a very important concept. We shall consider about partially ordered sets and partial orders and also equivalence relations in the coming lectures.